Hi everyone. Привет, добрый день, доброе утро. Thank you for coming here. My goal is to talk and explain you a little bit of coroutines. So intent is to explain the magic behind and the core concepts of it so that you are able to learn more and understand what's going on inside. So let's start. So the first, that's me. So if you see me around, come by, ask me a question. I'll be happy to talk with you. If not, you may tweet me and I'll help you remotely. Well, beyond that, I'm Eugene. I work at JetBrains, and I'm here to explain you something about coroutines. Okay, and before we start, I have this example which you've seen before, like while we were setting up here, and I would like to ask you to think what can go wrong here in this particular example. Well, so intent is we'd like to download something from the internet and we would like to return it from your web service or show it on the UI, whichever you like most. And the thing is that this is likely to be a blocking code. By blocking code, I mean that when we do some network call, we need to block and wait for network or library or something to download the data for us. And would it be okay? In most cases, it would be okay, and it would be enough. But something may go wrong. And if it goes wrong, someone would be able to spot the problem like that. If you see this, well, probably it would mean you'll be woken up in the night to fix this service or something, or your customers will be not that happy if you see the problem out of the blocking. Or it could be the problem like this. Have you seen this sometimes? Or if you do some more sophisticated network setup, it might be just the gateway timeout. It's not that fascinating to see that from the other services which we use when something is going wrong. Why? Because our threads can be blocked by some blocking operations, so all threads are blocked, and our application is no longer able to cope with the load because the threads are busy. Well, sometimes it may end up like this. Remember? Well, and on Android or iOS, you may see the notification from the operation system saying, oh, sorry, we have to kill it because it's no longer able to answer. But to be fair, on Android, you're not allowed to do network calls from the main thread. They assert it. Well, but I'm not the first one who say, okay, blocking might be not the best thing, right? And how do we solve it? We are here, we write the complicated programs, we know a decent number of solutions, dozens of solutions here. And one of these could be, okay, I would not block, I'll do callback, right? So this is a Kotlin language, so these are the brackets here means that you pass a lambda, right? So this is a little bit different from Java syntax, but I hope you can get it. Well, okay, we'll say, okay, fine. So please download the page and let me know once it's done. Well, if you do UI, you should ask yourself, what thread would it be where you have your callback? If it is the wrong thread, probably you have to do something before it crashes, right? Because you're not able to update the UI in the main thread. Okay. But with coroutines, it might be different. The only difference in this example is the suspend keyword. This is it. This is all you need. The fact is that this one would work in a way with the callback we expect it to. From the other side, the code is the same virtually the same as it was before. So we can understand what's going on. You don't need to know the fancy stuff to understand what the intent of this program is, right? Okay, the coroutines as the concept, it is not new. It was invented, I think, almost 60 years ago. If you go Wikipedia and you take a look on this explanation, it tells us that the concept was invented somewhere in the 50s and the end of 50s by Donald Knuth and Melvin Conway. They consider it a concept of a function which has not only their starting point and the return points, but also it is able to suspend the execution in the middle, preserving the state, the variables, the call stack, anything. And then the CPU is no longer busy, no longer blocked. So CPU can be used for something different. And at some point, we are able to resume this function so that the computation is resumed for the point where we suspended to go further. That's the idea. And if we see what we have for the JVM, we have a great project which is called Project Loom. So if you're looking for some insights on what's happening, it's really, really good to take a look on their wiki and see the explanation. And the TLDR would be, okay, the threads, historically, the threads are heavy concepts. The threads were invented as a part of the operation systems, not as a part of the languages. And for many years it was so. And then finally, in some new language, we have the concept of thread included. But in C language, for example, there is no thread support even today. So we have a library to deal with threads, right? And threads are heavy, and it's easy to explain. We have thread pools, we have callbacks, we have so many cool things to solve this problem, and we cannot start as much threads as we like. But the idea was really good. Start as much threads as we like and solve it. It's not possible, unfortunately. And asynchronicity, which comes with the threads, the fact that the thread is suspended at every random moment, it brings us to yet another set of troubles and complications. But let's step back and let's see some pictures. So for example, let's take a look at a picture how the CPUs and threads are supposed to work. So let's assume that we have 2 CPUs and we have 4 threads. And the time goes from the left to the right on this picture. So at some moment, the thread 1 decides is scheduled by the operation system to work with the thread with CPU 1, right? At some point, this vertical line says that operation system decides to say, okay, it's enough. Now we switch the context, so we store anything CPU related, the stack, the instruction pointer, registers, and then we switch to another activity, like say thread 2, and so on. This is operation system to decide. And I want to ask you to remember this picture, because now I'll show you yet another one with coroutines and threads. That's pretty similar to what we had before. Once again, this one before, and that one is now. So what I've done, I've replaced the threads as lines with a coroutine. And the coroutine is able to run inside the thread. So instead of CPUs, we now have threads. And once the coroutine have done anything, and it is a decision of your code, of the coroutine, to say, I figure, fair enough, now I need to suspend to wait for, say, network to give me the data to continue. So at that point, we have this vertical line. This is decision of our code, not the operation system behind, to do the suspend. And once some event happens, we do resume. That's the only difference. The pictures are so same. So it's like yet another layer over the abstraction here, right? To summarize, the context switch, which is invented, I think, 30, 20, 40 years ago, where you have one CPU and a million of processors or threads. The context switch is done by the operation system. It's done really, really frequently because the operation system tends to make all your threads run, right? And you have no control. Well, you have some magic, like say, my thread is a high priority, my process is a low priority. But it's only the magic. It doesn't guarantee you anything, and you still have no idea the moment where you are suspended. But still you have few cores and many, many threads, right? With the suspend points and the coroutines, the picture is opposite. That is you to say, okay, I'm done, now I need to wait. And that point where the state is suspended and the CPU is free and the thread is free to do whichever it likes. This is the difference. But as for today, we have the Project Loom, which is coming with a continuation support. And it's good to give it a try, to take a look. And I hope it will be included in the recent updates of the JDK, OpenJDK. There are several projects which you can Google, like Quasar or Pulsar, which do some bytecode transformation. Because if we are not able to do the continuation inside the JVM, we can only implement it their upper level inside our code. And okay, there are several projects which are more or less that. And there are many languages, not only for the JVM, which do implement this concept, like C# with async await. Have you seen C# with async await? Oh, it's Java conference, I'm sorry. Thank you for your hands. Are JavaScript or TypeScript? Thank you for your support. Well, Scala, Kotlin, Ruby, Rust, even in C++, it's common in the recent standards that's being discussed how to implement this thing. But this time I would focus on Kotlin. The Kotlin is by version 1.3. It supports coroutines inside the language, so it's really easy to use. It's open source, it's free to use. It's statically typed. It's not like the JavaScript, right? And the Kotlin, it's not only for the JVM. So with the JVM, it interoperates with Java, so you can have the Kotlin sources along with the Java sources. It supports Android. It supports JavaScript, so you can compile your Kotlin program with coroutines to JavaScript. And at JavaScript, it's really essential because in JavaScript, you have only one thread to work with. I'm not considering workers here. And it allows you to do the concurrent multitasking way easier than it is. And the native, so Kotlin has its own native compiler, which is based on LLVM, so you can compile your same code for, say, an iOS application. It's yet another talk to discuss all these things, so we go further and discuss the suspend function, because the implementation is independent from the platform. This is so how suspend function works. So in Kotlin, by the way, suspend is a keyword, and the fun is a keyword which you use to declare a function. It's only fun. So if you do Kotlin, you type fun recently, all the time, right? Okay, here it is again. So this is our solution with their suspend. And you don't know what suspend means, but you feel like it's a coroutine, right? And the suspend keyword in the language is a tiny, tiny thing which we included into the Kotlin, which does the magic behind. We have a tiny support in a standard library for this concept. And the rest can be done in the libraries. And we'll cover the most popular library, which is kotlinx.coroutines. This library helps to deal with the threads, their parallel execution, and all that stuff. But let's first start with a simpler example, an easier example. Have you ever seen the Fibonacci numbers? Oh, wow. This is the numbers like this below. But here's a hint for you, non-technical hint. If you need to convert miles into kilometers or kilometers into miles, just find the closest number in the sequence and pick the next to the previous one. 8 kilometers is something like 5 miles. You can easily build the sequence in your mind, and it's the way to convert. Like, just a cool fact. And then you can recall that it could be done in a Kotlin. But before that, now I need your imagination once again. How would you implement an iterator for the Fibonacci sequence? Like, think for yourself for a little. The moment you're thinking, I'll do yet another trick. I'll implement that one with their coroutines, with their coroutines builder, which is called sequence. So instead of explicitly implementing has, next, and next functions, which are supposed to be implemented for the iterable, or iterator, sorry, we do it with the coroutines builder, which is sequence. And we do it in a similar way. You may have seen it in their, say, C#, yield return, or JavaScript generators, and I guess every language so far from my list and others may have it. So I'll do the following thing. And just tell me, would it even complete? Or will it run eternally? Well, let's go step by step and figure out. So this is how coroutine is implemented, and this coroutines has nothing to do with threads. This is the only an explanation of the coroutine concept first. So the sequence function, this is something which creates us an iterable. And by the way, this syntax, it misses the parentheses. So this is a sequence, is a function, and in brackets, it comes the lambda, right? But the parentheses are okay to skip in Kotlin if it is the last parameter of a function. So this is just a lambda which is being passed to a function, nothing more. Okay, so this sequence function is from the standard documentation. It tells us that, okay, it takes a lambda inside of this really long type, and it returns a sequence, which is the same as a iterable. You're with me, right? Okay, let's go. So, and this yield function, this is an example of a suspend function in action. What it does, it is a function which is able to return the next element for our sequence and suspend execution of that block. Let's see how it works. But before, here's the rules. If you have an ordinary function in Kotlin, you can call ordinary function from it, but you cannot call a suspend function directly. You should use their coroutines builders, like sequence, to jump into their suspend world. Let's see. So to demonstrate the thing, I decided to add two print statements in this program so that we could see what's going on inside, right? And over here. And then on the right, I'll be printing out the console output to explain the concept. So the first step, it's a little bit before the println statement. What's happening here? So we say we would like to take 10 elements. That's a limit operator on every sequence. So it takes only 10 elements from a collection, right? And the for each, it tries to extract the next element from this iterable. So it calls either hasNext or next function. And to do so, the execution jumps into this block. So the sequence function actually starts evaluating this lambda for us, right? And their code flows step by step, here, here, here. Finally, we print the yield 1, right? Once we've done so, here comes the call to this function, which is yield. And at that point, behind the scenes, we exchange the call stack with a callback. Think about it. So, and for us, for this particular example, it means that we are able to return the element. So the state of this lambda is persisted. So we know somewhere that the f0, f1 is equal to something. And now we know where we stay in this function. And now we can suspend. So we suspend, the execution flows back, and we print got1. Then the for each tries to extract the next element of the collection. So the execution resumes. This is the trickiest part. So this lambda starts to run again from after the yield. And it goes. And it goes again. So it prints 2 on the screen. And it goes again. And so on. So it flows this interesting way between two coroutines altogether. So we can print the all elements of the sequence step by step. Well. So this was an example of the coroutine. Or that was it. And now we will build a little bit next layer to explain how we can use it for different use cases and examples which we have around us. And as for explanation, here's the diagram again. So on the x line, I have the coroutines or functions. The bottom line is a for each, and the upper line is the sequence. And the fact is that when the moment where for each asks for the next element, the execution jumps up to the upper row for compute. And once compute decides to say it's ready to give us an element back, it calls yield. So it's our decision to say what point where we would like to execution to be stopped or suspended or context switch to happen, depending on which term is closer to you. OK. So once we do so, we call yield. Yield return the execution back to the bottom row. So we continue the execution, and so on. That's the magic behind. And to summarize, the Kotlin coroutines, they have a suspend function, which is included into the language. And I showed you a demo with how the suspend function works in the most easiest and simplified example. It is not related into threads, but if you use threads, you can use it, combine it with a library to yield the results. And we'll see this library a little bit later. So let's back to this example. Again, we have the suspend function. We need to download something. We need to show it, right? This open function is a suspend function. This is something I haven't shown you before. This is it. So you say, OK, open is a suspend function. So the time we need to spend downloading the data, the CPU would not be used by this function. We have 2 pairs of that. And this is how you may implement the open function if you don't have any coroutine specific in your code base. And it's several lines of code. Let's go step by step to see what's inside. The first thing, when you do some download, you need to deal with a library, be it an HTTP library from the recent Java or your favorite another HTTP library, whichever you like. First thing you do, you post a task for a library to do some network for you. And you have a future, completable future, something where you can subscribe for the result. Because we do not like the blocking code anymore, right? And once you have your future, here's the tricky thing again. This is how you can implement your sequence function or your coroutine for multi-threaded programming. This is a suspend coroutine function. It's the magic. What it does, it allows you to exchange the call stack with the callback. So once this lambda parameter is executed, the CPU is free, the function returns, anything is no longer busy with your code. And to wake it up, you call either the resume on this continuation object or the resume with an exception. And so actually you subscribe, or here you subscribe for your future to have a result, and you pass this result to this continuation object. That is it. But no matter what we return from here, this is the backgrounds, the implementation part. There, it is still readable. Here we either have the return value from the open function or an exception. You don't need to reinvent a specific wheel, specific method to deal with the exceptions or results of your asynchronous activity. That's the trick. Okay, let's back to some more clear details. Let's say we do a blocking service. So we have something like this. We do some server-side, Spring Boot, Enterprise, whichever you like, whichever the way you call it, and say service B here is your favorite database, or something else. It's up to your imagination here. And what we do, the implementation of a given endpoint is to call free services and to aggregate this data. And the concept of the blocking, this GSP servlets, the servlet API, for example, the first version to say, the idea is that you do use one thread to process the whole request. And this thread blocks waiting for your database, the service A, service B, service C, weather forecast, I don't know what else. So you do block. And this is the easiest way we can write the program. So in my case, I just say use the println as the way to return the result from this implementation, just to simplify it, or just to play the CGI. Well, how it works? It blocks to wait for service A to work. It blocks for service B to work, say it's your JDBC call. It works for service C to wait. And finally, it aggregates the result in this trio way. And here we're done. Is it the best way to program? Thank you. You're right. If you can write your programs that way, just write programs that way. Don't overcomplicate. What we'll do, overcomplicate. So, and before we go there, I need to clarify my statement. How many threads are even possible? Any guess? Tell me. If I start threads like endlessly, how many can I have in my application? 10,000s. Tens. Sorry? Million? Any bets? 64K, 10 million. Well, you know your voters. Now here's the example. And you were close with 1 million. I wrote a program. So what I do here, it's in Kotlin, but the idea is that repeat is a loop. And what I do, I would like to start 1 million threads to wait for a barrier, and then I'm done. So any more ideas? Thank you. OK. Independently on how much memory do you have, you're likely to see this. For example, on your computer, right here. But please don't focus on your computer to implement it right now. And in my case, in my MacBook and a Linux desktop, I had these numbers. And it was like 64 gigs Linux and 16 gigs MacBook. The fact is that if you tune your kernel in the right way, you may have the different numbers, slightly different numbers. I did no tuning. So it means that you can only have 4K threads on macOS, 12K, 10K, it was quite close, thank you, are for Linux, not much, right? And then I decided that I need to do an experiment on Windows. On this graph, you see the time in hours to allocate the number of threads. So jokingly, if it is fine for you, it's only a joke. If it is fine for you to have your microservice to spin up for 2 hours, you have no problems because you literally can have the 500,000 threads. And the fact in my case, I forgot about this computer. So the next day I opened it up and it showed me the process crashed. It consumed all the memory, and there like 3/4 of the million threads were allocated. So if you have one day for your enterprise application to spin up, fair enough, you're done, right? And to summarize what I have, you cannot start as much threads as you like, so we've seen it. And even if you can start like 2K, 4K threads, if you would try to see how equally they are distributed, the CPU time is distributed, you would realize that there are some threads which are stuck. So like, say you have like 5K threads in your server-side application, and there would be some lucky winners who would be allocated to a thread which would not be executed on a CPU for a decent long period of times. But from the other side, if you would like to do the fair locking, the lock which tries to have a good distribution, it would slow down your application in several times of magnitudes. It's too slow, 100 times, 1,000 times slower if you do the right locking. Like, for example, if you do the reentrant lock in Java passing the true as in constructor, it would slow it down. Well, to summarize, unfortunately, we cannot use the most easiest example. If you are able to, use it. Don't overcomplicate. Well, what we do, we can scale application up. Are your application is able to scale? Who can scale an application easily? OK, so let's listen to the other solutions. We can try to do the callback-driven programming, or we try to do coroutines. So let's do this. And before we go there, this is an example of the coroutines. So I start 1 million coroutines in my example. And the outcome? The outcome, it works a little bit longer than 30 seconds, which is the delay in the middle, because essentially underneath, it turns out to be 1 million tasks in the executor service. That's all fine, right? And then 1 million tasks after a delay to resume the execution. It's again fine. So it works really 31, 32 seconds. That's it. So coroutines are not threads. Coroutines use threads to run. And you can allocate as much coroutines as you like. It's up to you. You no longer need to have a thread pools, anything complicated. You just spin coroutines the way you need it. It's as cheap as an object instance in your program. Well, and threads from the other side, threads are heavy. You need to do synchronization. You never know the moment where your thread is no longer running on the CPU and it waits for the next CPU spot in the operation system. The coroutines, you know the moment where you suspend. But the coroutines are running on top of threads. So operation system and the whole this magic is still there. Be careful, because if you do some global state manipulation from a coroutine, you may still need the synchronization. But if you do it inside the coroutine, you no longer need it. OK, a blocking service. How we do with the blocking callbacks programming? Have you ever tried programming with callbacks? I hope you do, right? I think you do. Well, never mind. But anyways, if we start doing it, we have a function with a callback, some parameters, and a final callback. Then we realize that it's a little bit more complicated, because we need either result or a error. It could be a function of 2 parameters. So in this line, it's written that we have the call function takes a lambda, which takes 2 parameters. Or we may invent a callback with 2 methods, like on error, on complete, or like in the Rx 3 methods. The whole thing is that in the callback-driven programming, we can limit the number of threads to something comparable to number of CPUs and say, OK, our threads would be busy processing the events, errors, messages, and we can have millions of requests being processed by tens of threads. Awesome, isn't it? And here a question. How would you wait for several callbacks, like say 3 callbacks, to complete and fire yet another callback? Think, how would you implement this with the context of the Java memory model, asynchronicity? It's really interesting task. And we jump back into our service, and now we try to re-implement it with the callbacks. So before we had this, right? This is a blocking implementation. Now we have something like this. What could go wrong? Well, actually, we need to handle cancellation, back pressure, error handling. So we have something like this. You don't need to read it. The essential part is here. Have you seen this in your code base? This? Do you feel like here? Well, and it's all fine, right? We are programmers, we're software developers. We are here to write this. It's OK. But if you would try to change a little bit this algorithm, you'd likely to remix it. And well, good luck to someone who would try to code review your change. That's all fine. And the fact is that I'm not the first one here to say that it's complicated. Everyone knows that it's complicated. Who knows what monad is? I would not explain you a monad today. The fact is that there are so many solutions to get rid of their nested callbacks. The popular one could be the completable future, or promise, or async await, or project reactors, lambdas, monos. And there are so many libraries which works the following way. They say, OK, I need to do some non-blocking computation in the right way. How would I do so? I'll create a pipeline in my language. A pipeline, no longer a program. I will create a pipeline, a mixture of lambdas. How would it be executed? I have no idea. But the way they would be executed is guaranteed that it would be non-blocking and is so good, so right. Well, this is an example of the zip function from Java Rx Java. This one waits for free streams to complete and fires the function free as the third long parameter to compute the result. Nice. If you would go and see the implementation of this one, it would be 400 or 500 lines of non-trivial, complicated code which deals with synchronization inside. It's good that it's hidden inside the library. And please don't try to re-implement such a code manually in your case. Use the library inside instead. Well, so this is an example how it would work. And it means like we need to learn yet another language to deal with this. We need to learn, it's called operators, the zip.zip, for example. These are operators, .zip, .map, .catch, .subscribe, .something, to deal with this new world. It's all fine, we can do it. And we can write the programs in this variant. But before we go further, let's see an alternative solution. Here it is. I, again, wrote the suspend keyword here. And again, I say that the call function is a suspend function. The difference is that this code is still easier to understand as far as I see it. So if I would bring you this code piece, you would be able to get what I try to do without reading this. Well, if you live in the world of the observables, probably you would easier read it. But I would spend some time compiling this one in my brains before I would be able to reason about it. OK, this is a suspend function. So dealing with the suspend functions here means that I can use the standard loops, standard conditions, function calls. So I can program the way I was learned back in the university like 10, 20 years ago. Well, how does it work? So I have this suspend call like this. When I compile it, this is written in Kotlin. Kotlin is able to generate the classes for the JVM, right? So some declarations in Kotlin are a little bit different at the JVM level. And we try to go underneath the cover to see. So at the JVM level, you will see the function like this. So instead of the suspend keyword, you'll see this fancy continuation parameter. And function no longer returns you anything specific. Instead, this callback is being used. And this continuation is something which allows us to exchange the call stack again with a callback. And the continuation by itself is the interface as follows. So it has the main one method, resume. So this is the point where you have your data. You call resume on a continuation to say, fair enough, now it's time to resume the execution of this whole call stack. The whole call stack, because once you exchange the call stack with a callback, the whole call stack is being recorded and suspended and kept in a heap memory. It's a heap object. So essentially, barely, the meaning is as follows. When I call this call method first time, the rest comes as a lambda parameter, and it goes to the continuation. When I call the second one, again, the rest comes into a callback. Of course, it is not so easy to draw if you have the loop inside, or try catch inside, or like function call inside, but the idea is that. And that is actually it. So, for example, if you would like to do async await, of course it is possible. It is not always needed here in the coroutine style programming, but of course we can do it. So here's an example with async await. A little bit longer, but now we can do async await in Kotlin. And the benefit here is that, again, is the same as the example with the zip. Here we call these three services in parallel, not step by step, no, one by one. And then at the end we do await. So which function here is a suspend function? Any ideas? So I hear async and I hear await. The right answer is await, because async function is nothing more than executor.submit. Essentially, it returns you an object which is similar to future from T in Java. And when I do await, I do suspend. So when I say await, the execution is being suspended to wait for the result to be computed. And if it is computed, I can go further and do this b.await. If it fails, I'll have an exception. So I can handle it by try catch or something. That is it. This is how you can do it if you do really need to parallelize these things. If you don't, use the previous example without this async and await. Okay. By this moment, I would like to show you how one can use the Kotlin X Coroutines library. This is a library which we do at JetBrains. And this library helps you to get the maximum possible value out of the coroutines and the concept. And this library has so many modules, so you can integrate it with any features, any async programming which you have. It's likely to be supported already. If it is not, well, it's good time to try and contribute. But in most cases, it's so easy to connect one with the other. Okay, so to start with, you add the dependency like this in your Gradle, Maven, or any build system, say SBT. And then you implement a small object. This is how you implement an object in Kotlin. So you implement one object. So what you essentially need, you need to say that dispatchers.io, this is barely it is a thread pool where your coroutines would be running. And this job object is a good lifetime for anything, so you can cancel it to kill anything which is running behind. And now we're here with a more complicated example of this presentation. And let me explain this one. So the first thing is the function launch. This function launch is again similar to executor.execute. This is the way how you can spin off a coroutine without waiting for it to complete, right? So it returns an object, a job object, so you can even cancel it if you like, or you can wait for it if you need. Well, this is how you start it. So inside this block, there's something which will go into a coroutine, which you've just started. And this is the documentation of this one. I decided to put it here and to say that the library is really awesomely documented. So if you're trying to figure out what's going on in there, just navigate or see the Java doc or KDoc to see how it is supposed to work, what it is inside. And actually, the documentation is a little longer because I have these 4 dots over here. So this is essentially the idea. So now I started. The async function is the way to start the coroutine which has some result. I decided not to put the documentation slide here because it doesn't fit the screen in the right way, in a good way. Well, this is how you start a coroutine, which returns the result, like open in the previous example, right? So you start the second coroutine here. We have 2. And then we wait for it. As in the previous example with async await, we wait for it, calling the result.await. This is a suspend function call again, so that it would suspend the execution to wait for the result to be ready, and then the execution would be resumed. By resumed, I mean that it will be rescheduled in your coroutine dispatcher, like rescheduled, like, again, executor service.execute, something similar to that. Okay, and this is the most powerful thing I decided to show here. This is the with context function. With context function tells us that we would like to have the lambda, which comes as a parameter again, to be executed within the different context, be it a different dispatcher, different object, different coroutine name, or whichever it is. So I say here essentially that let's launch the whole thing in a I/O thread pool. Then let's do some print, fine. Let's start an asynchronous activity to do some heavy work. Then let's call the show result function in the main thread because of the with context thing. And before we call the show result, we would suspend to wait for the heavy task to be completed. And this could be applied for your server side, for your client side, for like any sites, even for JavaScript. Oh yeah, and before we end with discussion, there is a really cool concept. This is something which is really hard in Go language. This is the structured concurrency. I have the link below. I would recommend you to go there if you would like to know more. The idea is you spin off the tasks in your executor, or you spin your coroutines, or you spin whichever you like. If something is going wrong inside, you need to find the way to kill the rest. So you start several activities. One fails. You no longer need to run the others. You should probably cancel this. And with a coroutine scope, this is a tiny function which you could use. The framework, the Kotlin X coroutines library, it guarantees you that it would wait for all coroutines to complete before it completes. And should one coroutine fail in the middle, anywhere, it would cancel the rest. It would cancel all other coroutines, so that you would not be spending your time for work you don't need. A comparison. If you start a thread, no one cares if you would kill it or you would wait for it, if you have an exception in the middle. Here it is done inside the library, so if you have an exception, that thread would be killed or stopped or waited for. This is the difference. Well, this was the Kotlin X coroutines library. You may simply Google for it, and you'll find this whole documentation. It comes with a really long read of documentation and the tutorials and stuff, so that you could give it a try and figure out how it helps your daily tasks today. But again, if you can avoid using callbacks, coroutines, all that stuff, try avoiding this. It is a layer of complexity, and we are all, as the industry, we are really good to invent the complexity and then to simplify this complexity. But first, proof you do need to go through this loop. Because if you could do the blocking application and it fits your needs, do it. Don't overcomplicate without reason. And solve some puzzlers to get introduced into the coroutines or non-blocking programming stuff. So try it, but be careful. Well, to summarize, we do use Kotlin and JetBrains really, really smooth, and there are in many projects. So for example, about 70 people is involved in just doing Kotlin libraries and the whole ecosystem around Kotlin. And we do have so many products which are written in Java for the JVM, where we combine Kotlin and Java together at JetBrains. For example, IntelliJ. Do you use IntelliJ? It uses Kotlin inside. If you don't trust me, open the IntelliJ community on GitHub and have a look. It's open source. It has an open source part where we do use Kotlin as well. Or yet another part about Rider, but you may ask me about the C# IDE and how to use Kotlin a little bit later. And there are many products which we have which uses Kotlin. Well, actually, I just like these logos, and I'm not sure if anything is included. I think I'm missing some parts. It's a good idea to update this one. Well, and to wrap up, it's good to give some references to something which could be good. And I see these talks really amazing. I do recommend you checking out these talks. And probably, so last year we had the Kotlin Conf, and one talk from this list is from the previous year's Kotlin Conf. This year we would have the Kotlin Conf again. This is a conference entirely for Kotlin. And there will be probably good talks about Kotlin and ecosystems. So just Google it, and you'll probably be able to see these videos online or offline. And the last thing, if you do Kotlin, well, expect fun. And the fact is that expect and fun, these are keywords in the language. And it could be an assignment to you to take a look and realize what mean expect and fun. But trust me, if you do so, you will have to write this in your programs too. So if you have fun, well, this is an actual fun. And that was it. So I'm happy to have questions from you. Thank you for your time.